Hey, welcome. Oh, sorry, wrong language. Hello, welcome to software testing. We're gonna focus on test effort assessment and the part of the test effort assessment that has to do with unit testing. But before we start that, I'm gonna show you a CS quiz because you've completed the first assignment, or most of you did complete the first assignment. I think it was like 87% or something like that, which is fantastic. Good work, everyone. And if you're still struggling with this assignment, if you have started and have not yet completed the examination task of this in this system, then you should continue with this. And I've written instructions in Slack, which you should follow so that you know what to do and what deadline. And yeah, this is not the examination task, but it's pretty close to the last task. And this is the practice task called test in isolation. And it seemed that most of the students actually completed this assignment, but did not really get what I wanted them to get out of it. So I'm just going to go through more or less the tutorial and what I think is the reason for having this task. And I think it's relevant also for assignment 1 part 2, because you're going to do a lot of mocking. And why do you do mocking, and how are you going to handle things that have dependencies? So okay, let's take a look at the tutorial first. So this is the case that we have a class name order. The order is a shipment order or something that someone ordered from a web shop or something like that. And the order consists of 0 to many order rows. An order row is perhaps a product and the amount of those products and a price for each item in this. So it could be like we have bought 3 60-inch TVs, something like that. That could be an order row. And it's in the same order as my new iPhone 8 something. But we only buy one of those. So we have 2 different order rows and the amount of products in each. Problem is that I have a buggy order. So perhaps like that. We calculate the sum of all these, and I've introduced a bug. So this code is buggy. And we also have a buggy order row. So this get row price should not be only get product price. It should actually be get product price times the amount of products on this order row. So the problem is that in this practice task, we only have 2 classes. But really, when you have a project, there can be like thousands of classes and thousands of tests. And it could also be that we have dependencies that stretches many steps. So you don't have just order to order row, but you have order to order row to product to something else to something else to something else. And if you have these dependency chains and some parts of it is broken, and you use the entire chain for a test of the root item, which in this case is order, then you have a problem, because you want each test to precisely pinpoint the problem. So if there is a bug in order, we want the order test to fail. If there is a bug in order row, we want the order row test to fail. In this case, there are bugs in both. But if I go to order, and I didn't save it, so it's actually corrected. But if I correct this and save it, and then run this and check the output, and didn't show any output. Well, then I would like the test suite to give me this output, right? So if I fix the problem in order, I want the tests of the class order to succeed. But the case I get actually is this one. Both the test for order and test for order row fails. And the test for order fails since the test is dependent on order row, and order row test fails because it's a problem in order row, so that is sort of fine. So in order to get this, I need to make sure that during test, or the test of order is not dependent on what order normally is dependent on. So the test of order should not be dependent on order row. It must be dependent on something else. So I replace order row with something that is a stub instead. So let's create a stub, and a stub is just, we extend order row, we create some kind of default implementation that cannot really fail, that is by definition correct. It does not even need to work as an order row. We don't need to create a correct implementation. We just return something, and as simple as possible, but this something is what we define as correct. So in this case, I just return 10, and that is defined as correct. So when I'm writing my test for order, here it is, order test, I should no longer use the order row at all, because order row can contain errors, and it actually does contain errors. And the second test is also dependent on the order row. So instead of using that, I'm going to use the order row stub. And since order row stub does not need any set amount and set price, I can actually, perhaps this would be better. You send it 2 instances, different instances of that instead. And then the expected value is 2 times what order row stub returns. And this is what we define as correct, and this sort of is what we expect this test or the order to do. So for the same thing, for should return price for 1, I remove these things, and the expected value is 10, because order row stub, if you only have one of those, it always returns 10 as the price. So that should by definition be okay. So I have some problems in run. I don't know what that is. But let's ignore that for now, because let's start the lecture on test effort assessment instead. Okay, test effort assessment. And I want to start the presentation. Okay, test assessment is really, how do we know that testers are doing a good job, or we as a tester are doing a good job? How can we assess that the time we spent on writing test or testing the product was time well spent? And how can we motivate to someone who's going to give us money for testing that we are doing a good job in this? How can we build confidence using test? How can we motivate the confidence that people are that we're supposed to give people in our test effort? And I'm going to mostly during this lecture focus on automated unit tests. And I'm going to add the part on manual testing, more or less, for another lecture on this. So let's take a look at the project called Yoda Time. And oops, where did it go? And Yoda Time is a pretty old Java project. It it replaces Java date and time classes. It's used prior to Java SE8, but the interesting thing is there are around 2,000 commits, 67 people working on this, and so it's a medium-sized project. Not that active anymore. I mean, 2 months ago, someone updated something here. 17 days ago, latest commit. So it's actually still active, but yeah. And if we take a look at this project, it's interesting for us because it has an extensive test suite. And there are some test classes. And actually, there are pretty many test classes overall. It looks great, right? So how do we know that these people, if we're going to use their code and we want that code to be correct, how confident can we be that they are doing a good job? In order to, yeah, so think about that for a moment and just write in Slack or raise your hand if you're in the room. How can I trust their product? Yes? Oh, maybe. From the information you've received so far, it's not that easy, right? So we need more information in order to be able to say anything. Test the tests. Send in the mutants. Yeah. I would like to do a code coverage with their test, if we have that access. Okay, so running the test is a good idea. I mean, if all these tests fail, then that means that it does not work, right? If all tests succeed, then we would like to know the extent of their testing. So perhaps we should do something like code coverage. And Therese also says something about mutants. I'm going to tell you a bit more about mutants later this lecture. So, okay. We've already also discussed verification, which was the process of creating some mathematical proof that something works, right? But for this larger project, that is not feasible. And we've also said that extensive testing, which was that for each position, so to speak, in the input domain, we create this input, we create a test case and make sure that is correct. And if for all these instances, we find a correct output, then we can say that Jota time is correct. But in this case, the input space is so huge, so we can't really do that. So we need to find something that is adequate, that is good enough. So let's say that we have a program, and let's take the requirement input domain as the x-axis, and the requirement output or behavior of the program as y-axis. Then each position in this is either a correct output or an incorrect one. So for instance, I've created one test case, and it goes through Origo of this system. So it goes through 0, 0. Actually, the dot looks like it's like a millimeter above 0. I don't know. Doesn't matter. But I've created one test case. So the code is executed once with 0 as input and also 0 as output. If that is correct, we can't really say that it's correct for any input because we have only tested it once. It was correct for that input, but we don't know. We need more test cases. So the old book Mathur told us this: the test for program PR is considered adequate if for each requirement in R there is at least one test case in T that tests the correctness of P with respect to R. So that sort of means that, okay, if we cover every requirement, so we need to cover all requirements, really. So if I create a test case for this definition, that would be okay, because I've covered sort of all the requirements. But even if I cover all requirements, that is not enough. We could still have other inputs that results in other outputs that would be wrong. I mean, I've just one case. So let's create another test case, and I've added a bar here just to show you that for another input, the expected output was also okay. And if you've taken a class in math, perhaps you're like, oh, I want to draw a line through these. And if the expected requirement here was actually to draw a line, so to speak, linear input, then perhaps we're done here. Or, so if the requirement or the implementation is so simple as a linear function, then perhaps 2 test cases on that linear function would be enough. Like the one that cuts the 0 axis of x is enough, and then if I take another sample somewhere along the line, then I know the angle of the line and everything, the k in the equation, right? But if the implementation is a bit more complex, then perhaps I need to add more test cases. So if this is the case, then suddenly we don't feel as sure as we did a minute ago when we had a linear function, right? If this is the correct implementation, the green line, then at least I would need more test cases in order to feel secure, get the required amount of confidence in this. So perhaps I could add that test case. I actually forgot the dot and just kept the bar here for, yeah, but you get used to my slides now. So perhaps we should have that one. Perhaps we need more, depending on the complexity of the thing that we're testing. So if we're testing something that is really, really simple, then perhaps we could have just a few test cases. If we're testing something that is more complex, more, complex, more if statements, so to speak, then we might need more tests also. So I'm just going to give you sort of the same idea, but with another image. And this is sort of the thing that I think of when I'm talking about testing. So the big gray cloud is all possible solutions for a problem. And if you take a sample like out here on the, perhaps I can do like this, out here on the right, then we have a buggy implementation. If I take a sample over here, then we have another type of buggy implementation. If I take a sample over here, then we have some other kind of problems. So these could be all the student solutions I've seen over the years that is wrong for some reason. And then we have, when we reach the inner cloud here, let's take the innermost cloud first. This is the correct solution space. So there can be multiple different correct solutions for any problem, right? You can write many, not infinite, because the memory in our computers do not take infinite, but almost infinite amounts of solutions that are correct also. We could always add a piece of code that does not really do anything to a correct piece of code, and then you get another solution that is actually correct. Right. So this is the solution space for the correct solutions. And then we have a lot of solutions, and actually, perhaps most of the solutions we create are in this light green area. And those are the solutions that are almost correct, or at least for some inputs are correct, but there are also other inputs that they are buggy, or they have faults, that we get something that we don't expect out of these. Okay, so is that pretty much clear? Then let's create a test case. So test case for me is a constraint on this solution space. So it sort of says that everything on the lower right side of this test case is a correct solution. All solutions on the higher left side of this test case will be detected by this test case as a faulty solution. So if I take any input, or if I run this test on a solution over here, this test will fail, and a solution over here, this test also fails. So it's sort of a way of finding out information. So we put these constraints, these test cases, and by running these tests, we find out if our solutions is in the gray area or in the correct, not in the correct area. But we cannot really say that just by running this test case that we're in this area. We could also be here, or we could be completely out of it, because this test case only says so much, right? So let's add another test case. And this test case constricts the solution space, the possible solution space that we're in. And it sort of tells us that, okay, with this test case also, we are a bit more sure, because we have eliminated faulty solutions. This is a bit weird image, because often the test cases are like we're actually just cutting away really, really small piece of this. But if we could, then we would do as little testing as possible, because testing takes time. And we would like these slices of solution space that we cut away to be as large as possible. That would be fantastic if we could have a minimal test suite. And perhaps we add another test case. And as you can see, this test case is sort of less effective in finding solutions that are almost correct. It's pretty good still, but solutions that's almost correct. So it's contributing to the test suite as a large, because we have a lot of tests or solutions over here that are no longer possible with this test suite. But this test case that we add after that actually does not contribute anymore, because we already have a better test case that fails all the solutions this one does, but also fails these solutions over here. So there are tests, and then there are better tests. Yes?
In our case, when we're doing like test-driven development, if we're doing in the opposite order, so you do like a not that good test and then do a better test, should we remove the old test or keep it as well?
Okay. So I get a question when you're working with assignment 1, part 2, and you're working in TDD, and you might create this worse test before the other test. And the question was, should I keep this test that is actually no longer contributing when I got this second test much better, that is actually finding all the problems? And no, you should not that. You should remove redundant tests during TDD, and you do that during the refactor phase. So if you can discover that this test, I cannot create code sort of that that is a bug that only one of these tests will. Yeah, if you cannot create a case of code that this first test, this line, is discovering, but that one does not discover, then If you cannot think of that, then you can remove that. Then it's just redundant, so let's not spend computer cycles, let's not maintain that code, and so on. It can be a bit more complex when it comes to TDD, and actually you have just one solution and you're thinking about is this correct or not. You're actually trying to place a position here, but I mean, yeah, so there is no reason to keep this one. It might not be that simple when you're actually sitting with two tests and trying to decide. Okay, so let's take a look at the code and find something that could be considered another test of adequacy. We had the adequate, good enough test suite, and Mathur had one suggestion that, okay, all requirements must be covered by at least one test for this program. And let's take another one. Let's say that a test T for a program PR is considered adequate if each path in P is traversed at least once. So then we say that it's not enough to have one test per requirement. We also want all paths to be covered through the program. So let's take a look at what that could mean. It's called path coverage. We have a pretty stupid program, but still on the right-hand side, and it says that if the input x is larger than 2, then we throw an exception. So the program stops there and throws the exception, and then perhaps we have exception handling in some other part of the code. And that is, we start over here. This is the if statement. And the if statement has a true and false. And if its value is true, then we go down here. But we could also, if x is less than 2, perhaps it's 1. If this is an integer, then 1 or lower. Then we go to 3. And 3 is the statement inside here. Since this is a do-while loop, this statement always happens. So we come down here, and we increase the input with 1. And then we go down here, which is the while loop. And the while loop has a true path and a false path. So let's say that we had a 1. And then we step that 1 up to 2, right? And while 2 is less than 2, that is false, right? Then we step down here. And in order to get path coverage, we would also like, now we've stepped from 1 to 2, and we have another test case, 1 to 3 to 4 to 5. In order to get path coverage, we would like it to also take the path 1, 3, 4, 3, 4, 5 at least. The sort of the same thing as we told you that I talked to you about before, where I had 1 as an input. That for path coverage as the adequacy requirement, that would be redundant if I add another test, because the path 1, 3, 4, 5 is also covered by 1, 3, 4, 3, 4, 5. So we've already taken all paths. So let's add like -1 or 0 or some other case where we need to traverse the loop at least twice. We could have different these adequacy requirements that we think of. So sort of what we're working with is coverage. And coverage is a mechanism that lets us measure on our test suite the coverage of our tool. So for instance, we could measure the path coverage, or we could measure other kinds of statement coverage or something like that. Is the code even run? So just to backtrack a bit to the first lecture, I think, if we're gonna, by a test, detect a piece of code that is buggy or has a fault in it, then we need to run that test, right? So coverage is a pretty good tool to actually know if the test or if the test suite is totally crap, or at least does what we hope that it does. No, not the last part. That it could do what we hope that it does. So, a test suite that has very low coverage, we would not trust that, because we know that during the test runs of this test suite, much of the code is not covered, it's not run, then we don't trust that. So coverage is implemented by instrumentation. And instrumentation means that you take a piece of code written by a programmer, and then using a tool, you introduce new statement into this. So this is a piece of code connecting to a database. Not sure what it should return, but you're actually introducing things into this code, and the programmer never sees this, it's just done automatically. And if I want method coverage, if I want to know if all my methods are called during test, then I just need to log once. I just need to log the entry of the method. So I just put it before each statement inside this one. It puts the name of the method into a log, and then I can just, after running the entire code, check the log. Has all methods in my program been run according to the log? And then I can find method coverage. Method coverage can be a bit, I mean, if we have an if statement, if we throw an exception or something like that, if we don't just have one basic block of statements, so that a basic block is every time we run this method, all these statements in the method runs together. If we have something that is not just that, if we have an if statement, we have different blocks of statements, then we need some more intricate type of testing to know if each statement. So we could have something like this instead, that we call, this, I don't know what this is. Yeah, it's probably that we have entered the method and then we put a log line between each statement in this method. So if we have many statements, we can have one log line between each of those. If we have an if statement, then we have a log line inside the if statement. We also have a log line after the if statement, so that we know that we exited it. Yeah. And pretty much you can build this kind of information out of it. So this is from the code in, I think this is the code in assignment 2, the legacy web server system. And as you can see, this is a coverage tool that I used on that code from with Eclipse. And as you can see, some of the lines are green and some are red. So the green lines are run by the tests during the tests, and the red lines are not. So we can see the method close is never called during a test, and the method write file is never called during the test. And we can see that the while loop inside that is not called either. Yeah, so this is probably statement coverage, that it shows that each statement is run, but it could be other type of coverage, I don't remember. So this could be pretty good for us as a tester. Okay, let's add a test for close. Let's add a test for write file, because we need that in order to know anything about that. Perhaps for write file, since we have a while loop, we probably need more than one test if we want this path coverage. There are different types of coverage. So I've already told you about statement coverage. Statement coverage essentially means that if we take our code and we divide it into different statements, then we want to know if each and every of these statements has been run or not. So for instance, if we create a new variable, that is a statement. If we put a memory or a number into that variable, that is another statement. If we have an if statement, that could be several statements in it. Okay, I've also told you what a block is. So an autonomous piece of statement that is always run together. So if you have like integer a equals 10, and then you have integer b equals 20, and then you have integer c equals 30, and they're just lines above each other, they're always executed together. Unless someone turns off the computer, these lines are going to be executed together. There are no if statement, there are no while loop, there is not an exception that cannot be thrown during this. Perhaps we could get the memory full exception thing, but let's ignore that for simplicity. So they are a block of statement that is always run together. So we only need to cover these. We only need to put a log line once for all these. Then you can have method coverage, and I've already said that. And you could have even class coverage. Which of my classes are run during the run of my test suite? You could even have component testing. So I'm not interested in the class level. I just want to know which components are used during testing. And this can actually be quite a good level of inquiry, because you want to know what components are my system, what components does it consist of, what components have I dependencies to, and stuff like that. So you can do component type coverage. We've already talked about loop path coverage, but not really loop coverage. So let's talk about loop coverage, and let's step back to this one. So loop coverage checks that each loop has been covered 0 times. We did not step into the loop. That is sort of impossible for a do while loop, but for a normal while loop or a for loop, you can not run the loop if the inputs are this one is not correct, then we're not running it. And that could be an interesting thing for if you run loop coverage. That is one of the things that you're after. 0 times, 1 time also. I just step through the loop 1 time. So if I input a 1 into this one, and then becomes a 2, right? And 2 is not less than 2, so we just step through it once. And then many times, if I add like minus 100 or minus 99, that doesn't matter. So what loop coverage says is that it should run many times. 0, 1, and many times. And that sort of, if you instrument to create loop coverage, then you need a counter. How many times? And yeah. Then we can have decision coverage. It sort of means that if you have an if statement, there is some kind of decision made. It's a Boolean thing, and you want that to be both true and false. It's not always that you have an else statement for an if statement, but you could implement that sort of coverage as you instrument the code so that you add an else statement for every if statement. I think this is the place to go to read about this. So this is sort of the thing that you should look at. And this one, pretty good at explaining different types of coverage. There are more complicated things like modified condition decision coverage. And you can read about this, like every point of entry and exit in the program has been invoked at least once. Every condition in a decision has taken all possible outcome at least once. Every decision in the program has taken all possible outcomes at least once. And each condition in a decision has been shown to independence. Whatnot. I just want you to get an overview over this and try to understand how it works, sort of. And you can see path coverage is also here. And this is the place to go for that kind of information. Coverage, is not a silver bullet for many reasons. So I'm just going to tell you a story about the code in assignment 2, because this is also a code example from assignment 2. And down below, we can see a coverage report. And we can see that for this class, header, the statement coverage is 100%. The branch coverage is 100%. I think I'm not sure, but I think branch coverage is if you have a branch that both paths have been taken. So if you have a statement, both the true and false have been taken, so to speak. But the loop coverage is down to 66.7%. And I looked at this report and I thought, okay, how can I increase this? And I found out that I couldn't. So let's take a look at the code. So this is a header class. It's sort of encapsulating different headers in an HTTP message. And I have an enum that's sort of telling me things about these. So we have host and content type and content length and stuff like that. So when we're sending information over the internet normally between a web server and a web client, we're having these HTTP headers that are not shown to the end user normally, but they are telling things about the HTTP protocol and the connection and what kind of information is sent and how large was that and things like that. And as you can see, there are many of these headers. So in my code somewhere, I felt the need to loop through these headers. And if I take loop coverage, and the definition of loop coverage was that we should run it 0 times, 1 time, and many times. And for some reason, I don't get the full here, because I cannot run this 0 times, because there are always more items in whatever I send into this, right? So I can never get 100% loop coverage for this code, because by definition. Then I don't know why it's giving me 66% and not 33%. Perhaps I have another loop that is more fully covered. I don't know. Is there some coverage types that are more standard or needed, or does that depend on the project? It's a good question. So let's take a look at this one again. If you're in the aviation industry and you're writing source code for an airliner, airplane, then I think, at least to some standard, you are required to have the MCDC, multiple condition decision coverage, level of coverage. Then they really want you to cover each path and all decisions are made, and that is sort of the most intricate one of these that I know of. So yes, it depends. And it's sort of, I mean, as a tester, I think that you should think, okay, I need the right kind of tools in order to find out if I'm doing a good job. And perhaps if you're going to show a report to someone, then perhaps it's, if they know what loop coverage is and you get a high score there, then you can show them this report. If they don't know what coverage is, perhaps you're showing them another value. If you're motivating your own test effort, perhaps you're taking another step. So it depends on the thing. Okay. I've also come up with that, at least in my code, some errors were really hard to create. It's sort of meaningless code, actually, unreachable code. And the reason for that is what I call double checks. That I have an if statement that checks something, and somewhere in the path, there is another if statement that sort of checks that again. Both can be needed. It's not always redundant code. And then you get unreachable code that never runs. And yeah, So some factory code, I've just written that as an example. I don't know if this, it's a bit old slide, so it depends on your tooling also. There can be code that your test framework is unable to run. Like a couple iterations ago, I could not run the main method with JUnit. In Java, you could not test your main method because it could not be run. So you had to like create a process and then start the actual program in order to test the program. I tried to do that. I think you can do that now. So it depends on the framework. Yeah. Factory code, yeah, if you're really creating things that are taking time to create, then perhaps you're not really testing them with your really fast test suite. Perhaps you're testing them over the weekend or whatever. So, so here are more examples of hard to test code or hard to show coverage of. But I think that we need a break now. So I think that we're taking 15 minutes off, and let's see you in 15 minutes. Okay, welcome back to software testing, and we are talking about code that is hard to show coverage for, and this could also be a bit about code that is hard to test according to my experience. And most of these things that are things that I've encountered in my efforts to test, and it not always need to be hard to test for you because you're learning mocking, and mocking sort of solves some of these things. But it could also be that you're not really allowed to change the code that you're about to test. You don't have that amount of control over the code. And perhaps the code has been written a long time ago. Perhaps the code is some kind of legacy code that you get in an assignment. Assignment 2. Yeah. But still, okay. So if you have some kind of resources like file system or databases or an API or a network, it can be harder to test these things and harder to show that we've actually covered our code, perhaps because we don't want to call that API. And if you're unable to mock that and replace that with something fake, then it is harder to test. It could be that it takes time, or that you don't have access to these systems. It could be that they need to be configured in a certain way. It could also be that you cannot replace this by dependency injection because there is no dependency injection in the code that you're about to test or that you get assigned to. So, and perhaps you're not allowed to introduce that. Shit happens. Other things that I've done my fair share of programming Arduinos and robots and things like that. So if there are special hardware that you need to run your code on, you need access to that hardware. You need to be able to get the output. Your output in these tests on that hardware is physical pins on the Arduino that turns on as like giving 5-volt output on a physical output. It's not that easy to test or show that this code has been run. There is no mechanisms for, there are mechanisms. There might not be mechanisms, I should say, on specialized hardware to run the tests in a way that you can instrument. And because that could be because the specialized hardware, perhaps I should show myself when I'm making gestures, the specialized hardware does not have any means to communicate back to your computer in a way that you can instrument and catch those things. Perhaps the memory requirements on this specialized hardware is too little. Let's hope you don't encounter such things. But it could also be things like you have multiple languages in your project. Perhaps you have an PHP application or a JavaScript application, and inside this application you have, oh the horror, a regular expression that does something. This regular expression is pretty much a piece of programming code that you cannot really show coverage in that code as easily, at least, because the coverage tool does only handle JavaScript or PHP or Java or whatever language you're using. And some of the things that I've encountered is it's quite common that you write your game code in C++, and you can write tests for that, and you can have coverage tools for that. But then you have some kind of scripting language, Lua or something, that is controlling the enemies, so that someone who is programming the actual game is scripting the enemies. It should first walk over to the door, and then it turns towards you and picks up its gun, whatever. And since that is scripted, you cannot really have coverage of that code using the tools for C++. Then you need some other mechanisms for testing that Lua script. So this is not impossible, but it makes it harder. Data-driven code, like for instance, you have a lot of XML or JSON or whatever, as input to the code, and that configures the code and it gives too complex input. So if you like build up the objects using XML or whatever format, then and there are too many combinations, then it's very hard to actually like know that you're doing good here. I've also encountered like iterative or recursive functions that are also harder to test. Recursive because we need a coverage measurement that can handle recursion and say that perhaps we should recurse 0 times, 1 time, or many times, but really it's not available. Yeah, the things that I've encountered are like simulation games and neural nets, where these are problematic. Neural nets can also be problematic because you don't know the output of the neural net is not that easily to decide what is correct or not. Yeah. So it's not always easy peasy. Okay. On the same path or on the same track is from test unreachable interfaces. This also depends on your framework and your programming language, if you can handle this. For instance, private methods. Should we create test cases for the private methods? If we create test cases depending on the kind of programming language and the kind of test framework, this may or may not be allowed. But the general case would be that from the test suite, which is another class, then you cannot call the private methods because it's another class. Then there are mechanisms that can allow that anyway in some cases. I think that in C#, some Visual Studio testing framework where they like automatically created code that fixed this so that you could create tests for your private methods. What I say is that the public methods should be tested in a way that the private methods are called and that we get coverage in those. Then we could, if the test framework allows, create specialized test cases for the private methods. We could, if that mechanism does not exist, we could raise the reachability of those methods, like creating them to be protected instead. And then we inherit from that class and add some mechanisms so that we can call the protected methods. We could even open them up, oh the horror, to become public, and just for the sake of testing. But now I think that we're starting to reach things where we're doing things to the system under test code that is not good for the system under test code, but is only good for testing. And I think that is a slippery slope, dangerous thing. So we're doing some things just because of testing, but perhaps this is too much. So another way could be to create new classes instead of these private methods. And then you create public methods in those classes and stuff like that. So you redesign the system. You're still making, I'm searching for the English word for eftergift, but you're doing stuff just because you want to test it in your system under test code. And we wish that we didn't need to do that, but if testing is important enough, then we need to do that, and then we do it. Right? It depends on what is at stake. Yeah, I don't know if this is solved, but a couple of years ago, like the Java console could not be mocked. I think they probably have solved this. If this is the case, perhaps you create a wrapper. If you have an API class that cannot be mocked for some reason, because it's final or whatever, and the mocking framework perhaps cannot reach or mock final code, then you can wrap that API. You create your own wrapper class around that API, and then you mock that one. Yeah, so this Daniel Alm writes, for Java at least, you can have test classes in the same package, which allows for testing package private methods. Great, thanks. Okay, while inspecting other people's test suites, I have found that some of these they have smoke tests in their test suites. And if you remember smoke tests, it was to run as large part of the code as possible. You run it automatically, because this is automatic unit test we're still talking about. And then you check if it crashes. Does it throw an exception or does it crash? And then, so it's, that was a smoke test. We don't have really any condition in the test. We don't have an assert. We don't check any mocking verification or behavioral testing. We're just looking for if there is smoke, so that we can extinguish the fire. You can read about smoke testing under that link. And from an assessment point of view, these smoke tests give high coverage, but they don't really test much more than that it does not crash. So they can still have value. I mean, these testers that wrote these tests that I've inspected at least thought that they had value. What if we start the game and then we stop the game almost directly? Does it start? Does it stop? What not? They found it valuable, so they have some kind of value, but it's hard to, if I run the test suite with coverage and include that test is going to include a lot of code that is perhaps not tested enough, but the coverage measurement is going to show that. We could have in-code asserts. That is, in the beginning of a method, we can check by writing, and now I'm talking about the system and not the test suite. We could have a lot of asserts in the systems that checking that different inputs and stuff like that, and that we're not we're not in an invalid state. It could be a precondition. That means that input or the state when we start a method is correct. It could be a post condition that checks if the output was correctly during some, and it could also be an invariant. An invariant is sort of these things that if you, invariance is a set of conditions that always should be, that should hold whenever this class that you're testing is handing over the control back to the other parts of the system. So invariant should hold before this part starts to run and after you have returned from that. And then you can run this and you can you can have this invariant method called all the time and during the smoke tests. So I'm not saying there could be asserts, but these asserts are not in the test suite. So this is a bit complicated, right? We can have tests and they could have different types of value, and we need to make a decision if we want to include those tests when you're running coverage measurements. And the decision is made from a conscious decision by some tester that, okay, why do we want to include this and what does that mean? Perhaps I would suggest that if you have smoke tests, that is fine, but you don't have them in the test suite for which you run the coverage measurement. But I mean, really, it's up to you. So the test could look like this: void run the system, and we call run on system, and then we don't do anything. If this test throws an exception, the test case crashes. So, and I've talked about the next concept on Slack, so just copy-pasted my answer on Slack just to make sure that you don't miss it. These are also about tests without asserts. So think of this. If you have a constructor, and if you send the constructor the wrong input, then it throws an exception. It could be that the constructor only should take positive integers, and you have a behavior that it should show that it should throw invalid input exception if the input is negative, like that. Then you write a test for that method that checks that we expect it to throw an exception, but you also want to test the other case where it does not throw an exception. But in this case, it's a constructor. It does not provide any output. So what you can do is that you create another test case that you just call new and the class name. You just invoke the constructor, and then you don't do anything. You don't assert anything. You don't need to check really that new returns an object, because new always returns an object unless an exception is thrown. And that second test is only valuable if it exists together with the first test that checks if an exception is thrown. So even if it does not have an assert itself, the other test has an assert, and these two tests together has value. I call these complementary. I've called them negative tests. And I think that these have value. They contribute to code coverage. I think that is fine. I've put an example here where you can look at the die clause, which should not be sent to null. Sometimes, in the case that I told you about, and also the case here, we can solve this by having more type safety. So you can say that for the die example in behind me here, then you could have that it actually must take a die object that is not null, and this is available in some programming languages and some it's not available. Yeah. And then you don't need to check that that test case becomes invalid because the code does not have that problem, so to speak. Okay. Now we've sort of done with the normal code coverage talk. You've learned that the different types of coverage, and that, okay, at least we know that the right header is called now. But we miss an important part, and that is sort of the assert statement. What does the assert statement do? Assert statement is actually where we do the comparison between what we expect and what we got, the actual to the expected. And we talked about that this should be done by the oracle. Someone is going to make a decision on this. So even if right header is called during tests, we don't know that it works. So we need to come up with some mechanism that can do that. And the first mechanism is sort of what I do to you, what I've done to you during your assignments in CS Quiz. So let's start in that end. In CS Quiz, you have a system code that you got, and you also have your test suite. And my endeavor was to test your test suite. I call these tests that I write meta tests. They are pretty mind-boggling sometimes when I write them. And what I do is actually I have a faulty implementation, which I call a mutant. So I create a version of the code that you tested in your test suite, but it contains a bug. And your test is good if it finds this bug, and your test is bad if it does not. I also need a correct implementation so that your test should pass the correct implementation and find the bug in the faulty implementation. It should pass that and fail the faulty. The versions with bugs are called mutations. And there is an automated way of doing this called mutation testing. And I think I have a code example on the next slide. A mutation testing creates a mutation score. And the mutation score is the amount or how many % of these faulty versions that your test suite can detect. So it's sort of your faulty version detection statistics. We change the system under test and we check if the test suite we've written catches that or kills that mutation. So let's say that we have this implementation should throw exception. Oh, this is actually a test. And I need a line in the system under test. So on the right hand side, there is a line in the system under test. So if we write input, or give it input 5, that is above 4. So we should get an exception being thrown. So the test for that is on the left hand side. So let's think, is this a good test or not for this? It reaches the inside of the if statement, right? Because we send it a 5. And yeah. So if I create a new version where I mutate the implementation by changing the larger than to a less than, that is a mutation that could be easily done automatically. I could create these mutants automatically. Let's replace some operators. That is a mutation, mutator, I think, or something like that they're called. And this mutation is actually discovered by the test to the left, because if I send it a 5, there is no longer an exception called. This mutation, is, however, not found. So for this input 5, it looks like if we run that test on that code, we don't discover the mutation. And the problem with this is that I only have one test. So this shows the need to add another test. What if the input is 4? If I had another test case with the input is 4, then I would have, like that, then I would have improved my test suite's ability to detect mutants. Because it should not throw an exception, right? And let's take a look at the last one here. Take a look at the last one and think about that mutation. Ignore the image and the colors. Can we detect that? Can we kill that mutation? Given that I is an integer. Yes, no, maybe? It's a mutation, right? We've taken the code, we've changed the parameter, we also changed the number. Can you create a test case that finds that? The problem is, since no one is answering, I'm going to answer it. Does anyone have a feeling? Okay, I'm going to answer it. So if we send it a 5, then it throws an exception. If we send it a 4, then it doesn't throw an exception. So it's the same behavior as the original implementation. So this kind of mutant is called an equivalent implementation. So it could be a true equivalent implementation, and that means that in this case, the last case, we had a true equivalent implementation. That means that for any input, these two versions of the program gives the same output. So they're both correct. So we cannot distinguish those. And if you're creating a mutation score, then this becomes problematic because you create mutations automatically, but you can never decide if these versions are actually the same or not. That means that the mutation score you create, and let's take for this one, we would get a mutation score of, we've created 3 mutations. The first one was detected, so that is 1 kill. The other 2 was not detected, so it's we find 33% mutation score. A test suite where we added another test case where we send it to 4 and make sure that it does not throw an exception finds 66% of the mutations we've created because we find 2 out of 3. But 66% sounds bad, but really we have a equivalent mutation. So if we're going to use mutation score to evaluate our test effort, then we can do that, but we must remember we can get equivalent implementations. Equivalent implementations could be relative to input, and that sort of means this last one over here. It's for this test case, we don't detect that. Yeah. Okay, let's ignore that image for now. Or perhaps I should say something about it anyway. So this is a piece of code. Each vertical line is a statement in the code. And then we have a test suite, and then we have mutations. So the white, I think, is statement coverage. We can see that most of the lines are covered by the tests. I don't know why not all parts of this are not covered. I think perhaps one test case. I think this might be one test case. So the white lines are things that are covered, and then we can guess that there are a lot of if statements or something like that. The red ones are lines of code where we, and this is where I stumble a bit, we get mutants where we don't kill them. So around the middle somewhere, we have a piece of code which is not well tested. We should add more test cases for this piece of code. Okay, so when I learned about mutation score, then I thought about what if we could create a better coverage measurement that allows us not only to see if a line of code is run, but also if that line of code is like tested by an assert statement. Then I made an implementation using something called dynamic slicing. And I did this, I think, in 2012 or something like that. And I thought, okay, which instructions actually affected the assert's outcome? And then if an instruction has affected an assert's outcome, then we call that covered. So if you have the code to the right, you can see that it creates, we have some input y, and then we have a local variable x. And then this line here, print, is using the local variable x. It is called, or every time we call this method, so it would be covered using statement coverage. But if I have this test over here, do calculate, I send it a 1, actual becomes something, and then I assert something, then this statement over here in no way contributes to the success of this one, right? Because here we don't change the value anything, we're just printing it. So this line would be statement covered, but not checked covered. In order to get it checked covered, I would need to check the output. I would need another test case that checks that X is actually printed to the console. Right? If I had that, then that line would be checked coverage. The other lines here, if I send it a 1, then Y is 1, then X becomes 4, right? And then we have a 5 is larger than 4. Okay, and we had, no, we sent it to 1, right? 1 is larger than 4. No, it's not. So we don't go in here. So both statement coverage and checked coverage won't include that. And then return statement is always included because we need the value back and stuff like that. Okay. Checked coverage was actually done a year before I started to try to invent it. So I think his name was David Schuler who did this, and I called it assert coverage and he called it checked coverage, and there was just 1 year in between. But he did it first, so I cannot really take credit for it. So that is why I call it checked coverage, but it's a funny story. So checked coverage, the tools for that is sort of growing. I have not really looked into it in a couple of years, but for assignment 3, you could, if you would like, to check up on checked coverage and see if that is grown to something. And then you can tell the rest about us in assignment 3 because you're making a short 5-minute video about that paper. So that could be a suggestion. Checked coverage also have some problems. We cannot assert things that did not happen. We cannot find paths for file databases and other languages. Here is more of those brilliant colors. Hi.
Didn't understand the mutation part on the previous.
Okay.
Yeah, the last one. Greater than or equal to 5.
Okay.
So what do we do in that case?
Okay, there is no way. Oh, okay. I'll get the question on the last case where we have the equivalent mutation. And what do we do? How can we understand this? In this case, I larger than or equal to 5 is the same as I larger than 4, for integers at least. And this means that this mutation is actually correct. It's equivalent to the implementation we had above, and there's nothing we can do about this. We could do exhaustive testing and find out that these two are the same for every input, but that is still too high costs. And this is an unsolved problem. And you need to, with current mutation score implementation, you need to live with this. This means that, I'm not sure about that, but if mutation score of like 80 or something like that is a good mutation score. And then on the image, I've shown you that Instead, if you're on the image we can see that on some cases we are not doing very good at finding mutants on those places. And this is sort of the same kind of visualizations that I used before. And what I've learned here is that I created a very simple test suite. No, a very simple implementation, and that was about triangles and math and stuff like that. And then I tried to create a test suite which fully covered this in all ways possible. And then I examined these different types of coverage on this. And as you can see, checked coverage for my tests, written by a professional, in my tests, statement coverage which is white, and checked coverage, which is yellow, is almost always following each other. There are some cases, and I'm going to see if I can find it. The first one I find is over here, then statement coverage. We have statement coverage, but we don't have checked coverage. And over here we have the same. And over here we have a position also where there is no checked coverage and stuff like that. So I would say that while checked coverage seems to work in a sense, if you have a good enough test suite, then you mostly have problems with equivalent implementations, according to my... no, I'm mixing up things in my head now. If you have a good enough test suite, then you don't really need to look at checked coverage, as far as I know. Then I did this on the on other test suites. And for instance, the Yoda time test suite. And I ran their test and checked mutation score and checked coverage score on these also, and found a different image. They had a lot more smoke tests. Tests that ran a large part of the code, but really didn't assert anything about that part of the code. So, and in this case, my conclusion was that if you create your test suite carefully, perhaps by using test-driven development, then you're getting good tests, and I would consider these good tests. But if you're just ad hoc testing, and you're just doing it because you want to raise your statement coverage, perhaps, and you're not really thinking about what you assert, then you're gonna get bad test suites. Yeah, it could be interesting if there is any good tools for checked coverage nowadays. It's come a couple of years, perhaps it have overwon the problems that we had a couple of years ago. I have not looked into that. Okay, so what does Kent Beck says about assessment in TDD? The output of running TDD on a project should be a minimalistic test suite with high coverage, because we don't add code without adding a test first. It should be minimal because we only test, when we add a test, it should always get read first. So we never add a test that is redundant. We could, however, add a test that makes another test redundant, and then we should remove the other test if we find out about that. So what he says that insufficient coverage is a sign of badly designed test instead. So we should, with our process and the way we write tests, be mindful of how to write this, and this should not be a problem if you're good enough. And it's a bit dangerous. And the reason for me adding coverage measurement into assignment 1 part 2 is for you to reflect on this. Why didn't we cover this when we wrote this test? And you're welcome to run mutation score also. It's not a part of the assignment per se, but I mean, that could be fun. Yes. I think that is sort of it for today. Are there any questions? Okay, then are there any questions on assignment 1, part 2? So next lecture, I'm going to start with the parts that you need for assignment 2. And let's keep the discussions on Slack on assignment 1, part 2. Can you talk about assignment 2? I will talk about assignment 2 next week. Assignment 2 is really that you get a legacy system, and you get a scenario, and then you're in groups, supposed. You form your groups. It could be just you, if you want to. Do testing. You have a budget, which is, I think, the number of people in the group times the number of hours, something like, I don't know. It should state it pretty well in the assignment description. So I think a good idea would be to read up on assignment 2 until next lecture, and then I can answer questions on it. Great. Thank you very much.
Anton?